Hello, my name is Jesse Chotiner. I am doing the Fluid Mechanics Summer 2025 ANSYS Fluent Project 3. I'm in a partner group with Connor Freed. I already did the Inviscid video with the geometry and mesh. I said Connor would do the other two. Unfortunately, his PC is not as good as mine, so I will be running the Laminar and Turbulent. We are using the same exact geometry and mesh from that video, so please check out that video if you want to see the process for that. But we are just going to put in a fluid flow fluent here. And we're just going to drag over geometry, drag over mesh. And that should all be good and set up. So we can just click setup on edit. We're going to do double precision 4, that's our max. We're going to click start. And we'll give that a second to open up. Alright, so it's looking good. We're going to go to models. We're going to go to viscous. We're going to go to laminar. Click laminar. That's all good. Materials, fluids. The parameters we decided to do for laminar are 1 density, which is the same as our Inviscid, and we changed our viscosity to 0.05. Change that, create it. Good. Make sure that fits in our surface body. Yep. And when we go to inlet here, we're going to make our velocity the same as before, as 5. If you do Reynolds number with those parameters, you get around 100, which is a pretty low Reynolds number, but it gives us the best results for laminar, which we can explain. We're going to check wall outlet is probably 0. Stationary wall, no slit. Let's actually check that. Alright, cool. Gotta go to reference values. We're going to click inlet. Looks good. We're going to go to methods, and I'm actually going to change pressure to presto, but I'm going to keep the scheme as coupled. That gave me the best results for this mesh and what we want. So we're going to drag coefficient, print to console for cylinder wall, just so we see that when we run it. We're going to click, actually, hold on, let me, give me a second. Alright, so I just re-added it to name it drag coefficient, so that's good. So methods are good, definitions are good. We're going to go to monitors, and we're going to switch our residual, same as Inviscid. That's not what I wanted. Why is it capital? There we go. 1e -6, 1e -6, 1e -6. We're going to click OK. We're going to get rid of monitors. So yeah, so we have our method set up, definition set up, monitor set up, inlet, Reynolds number good to go. We're going to click initialization. We're going to click initialize. And it's going to take a second to load. Give it a second. Alright, so the initialization is done. We're going to go to run calculation, and we're going to do around 1,000 iterations. And it should give us good results, even if it doesn't converge that way. Give it a second. Alright, so we're going to click calculate. And click calculate. And I will leave it unpaused just so you can see it start running when it does. Alright, as you can see, we're running the drag coefficient here, and we're running our scaled residuals, and they're converging very nicely. So I'm going to pause it here, give it a second to run, and we will see what happens. Alright, so the calculations have stopped. I'm going to give it a second to process it. Cool. So calculation complete. First thing we'll look at is our residuals. You can see they converge very nicely, and our drag coefficient also converges. And we get one about 1.11. You'll notice when we do the drag coefficient later that as long as it's less than this one for turbulent, turbulent is less than laminar, shows that there's more drag with laminar, I believe, so that should be fine. And what we're going to look at here is two different plots. So we're going to first plot our velocity magnitude along the cylinder wall. It's 0, which is correct because it's the boundary layer and it's a no slip condition. Going to look at the coefficient of pressure, and we save that, and you can see it's a nice little smooth line that goes on negative 0.8. I believe the ideal case is that that goes to a little -1, but when you compare it to the turbulent, you'll see that that curve is way below, or excuse me, above the laminar. So that should be good for our velocity, pressure coefficient, and drag. So we're going to exit out here of our setup. We're going to click OK. And we're going to go into our results to show the pressure contour, velocity contour, and the streamline contour. Alright, so that exited out. We're going to go to results and get that running. Alright, so we're going to create our contours first. So we're going to create velocity contour. We're going to click, that's fine. Symmetry 1. Velocity and 1 of 10 contours just to show it pretty well. And if we click on our Z, we can see we create a nice region here. So this is our wake region where our velocity is 0. And you can see the layer kind of expands out. And again, this is a small Reynolds number. So we'll keep it at that. And we'll turn that off and we'll create a pressure contour. Good, we're going to do pressure, we're going to do symmetry 110. And as you can see, we have our stagnation point at the front, high pressure, lowest pressure at the top and bottom, and we maintain somewhat low pressure after it. It's not much of a wake region. It's a small Reynolds number, but it still shows that there is lower pressure compared to the Inviscid, which is just completely high pressure in the back. And the velocity shows us our wake. And if we do our streamline here, do surface streamline, symmetry 1, we'll do around 1,000, just so it looks, has a decent amount on it. And as you can see, we have these vortexes here, which aren't really like truly vortexes, but it shows you that the velocity is 0 around here, which is the same as our velocity up there, and that the wake region is very big, right? There's a big gap here of almost like nothing in it with the high pressure here, and the velocity just goes around it. So this creates a lot of drag and a lot of from the pressure. So that's our laminar, and it's pretty straightforward. Again, you can mess around with the Reynolds to get your vortices and stuff, but we're going to click exit out, and we're going to create a new, actually, we're just going to go into setup of this one, and we're just going to change it to the turbulent that we did before. It's nice as most of our stuff is set up. We'll have to change up some values. Alright, so we're good to go here.
We're gonna switch our viscous model, and I found the best luck with the Spilart, so we're gonna use the Spilart. Oh, that's for your acid. We're gonna go to materials, fluids. We're gonna have to change our viscosity here. So the one we went with is 0.00001, so much lower than our laminar because we need a higher Reynolds number. Make sure that switches to our surface body. Perfect. It's the same value. Boundary conditions, inlet. We're going to change this to 6, and the reason we do that is if you get your Reynolds number, you will achieve one of around 600,000, which is above that 500,000 transition period. So it gets us into more turbulent area. Click our outlet. Looks good. Click our wall. Should be stationary. Yep, it gives us some more options here because it's the model, but that's fine. Keep that there, keep that there, keep that there. And we're going to go to reference values, and we're going to go to inlet again. Set that. Methods. So we're actually not going to do pressure this time. We're going to go back to second order. Again, this is from the results I got, and it made it look nicer. Report definitions is the same that we have there. Monitors are the same. And the plot is actually the same, but obviously we don't need to plot it now. So we're going to click initialization. Boom. Perfect. Run calculations. We're going to run them again at 1,000. This might take a little longer to converge, but I will start it, and I will leave it until it starts, and then I'll pause it. Started much earlier. Drag coefficient starts at the bottom because it's turbulent. And here's our scaled residuals. Get the nut as well. And I will pause it and come back when it's done. Alright, so our calculation has completed. We're going to take a look at our residuals. They did take all the time, but they did converge somewhat nicely. If we look at our drag coefficient, we see we have 0.46, which is good because that is less than our laminar and makes sense compared to it. The drag graph. And we're going to look at the same exact plots as before. First, we're going to look at velocity, cylinder wall, click, 0, same case, boundary layer. Why is steam popping up? Don't worry about that. We're going to go to pressure, coefficient of pressure should be similar. Boom. As you can see, turbulent goes down a lot more, and this one is going down almost to -2 CP, which is good because it should dip down longer to our laminar. It should end. This should be above our laminar, but in our case it might not be. But this is what's really important. It shows you that the pressure coefficient and the velocity is lower at laminar than it is here. So that's good for that in our velocity and our drag. We're going to exit out of here, and we're going to show our contours in post-processing. It should already be there from our previous one. And we'll start with velocity as well. Got a second to load. Alright, cool. So let's just start with velocity. So as you can see, we have a much smaller region of wake here, and it converges, or doesn't go all the way out here. It stops, comes back in, which creates a lower area here, or a small area here of low pressure. And the velocity obviously is same as the laminar, kind of, it decreases. And here's the pressure. You can see there is a higher pressure around the back than in the laminar. And we can compare this to our laminar. So here's the turbulent flow that you just saw for pressure. Here's the laminar. You can see that the pressure at the end here is greater, or lower, I should say. And here, it's a little greater. Right here, it's like -6. Here, it's around -2. And that creates a smaller wake region and a smaller drag, which is why the drag coefficient is different. And if we look at our streamlines, it also shows it. We got one vortex here. I believe that's somewhat correct. There could be vortexes that form because of the region. And obviously the big thing is this region here we'll compare it to the streamline for the laminar, is much, and the reason it's not the same is this one doesn't have as many contours as that one. But if you add more contours, another vortex will show up. But the overall gist is this region is much bigger than this streamline region. And yeah, that's pretty much it. We'll go to here, so to our document. And these are the values we use for laminar, turbulent, and viscid. Shows you everything we went over. The velocity distribution, you can see the laminar and turbulent is along the same path. It's 0, so it stays there. And then viscid goes all the way up. And if we go to the pressure, which is not fitted here for some reason, see that our, just move this down here, that our laminar is below here, and the turbulent does increase a little up here. Tried to fiddle around with it. These are the best results I got for laminar. The turbulent could maybe move up a little more depending on the Reynolds number. But overall, you can see this pattern is what we want to see in the middle. And yeah, so that was the laminar and turbulent. Again, it is the same mesh and geometry from the Inviscid, so please check out the Inviscid video to see the mesh and geometry process. But other than that, that's the entire Fluids Project 3. Thank you.